The premise of this research addresses a growing demand for a hydrologic classification system that allows a broad-scale assessment of how watersheds functions with regards to their landscape and climate inputs. This approach allows you to really understand watersheds function hydroclimatically and also then identify which watersheds or which type of watersheds are going to be more sensitive to stressors such as climate change or landscape change, and also really begin to quantify or tell you more about the timing and magnitude of water that's available for ecosystems or stream systems. So the premise of the work of the climate change piggybacks onto an Oregon, some previous work that looks at Oregon's hydrologic landscapes. So for this, we focused on Oregon, and the state of Oregon was broken down to over 5,600 subwatersheds or assessment units. Those assessment units were then classified based upon these 5 inputs. And again, what that gave you is a hydroclimatic classification system for each one of these 5,600 assessment units. Now at the state level, it looks kind of cluttered with all the polygons, but if you look at a more local scale, you see what I'm talking about. So this is, here's the peak of Mount Hood. So these are the different classification systems. You see the western slope of Mount Hood is classified as a much more wet, winter dominant or spring dominant system, whereas the eastern side of Mount Hood is a much drier and has stream flow is going to be a little more muted. So these hydrologic landscapes were developed for the climatologic record from 1971 through 2000. And what we want to do is understand how are these hydrologic landscapes, how are they going to change in the future? Or how do we think they're going to change to the future when we have changes in precipitation and temperature and the resulting effects in potential evapotranspiration. So how do we go about doing this? The analysis used 6 different climate realizations based on 2 general circulation models. The ECA model is going to be most sensitive to increased CO2, meaning that it's going to have a greater response to increased CO2 as compared to the PECA model, which is at the lower or less sensitive. We ran it for 3 different emission scenarios, ranging from a high level of emissions to the lower level of emissions that are listed accordingly. Again, the original classification was based on climate data from 1971 through 2000. The climate projections we're looking at are from 2041 to 2070. Just a kind of a key term that I'll be using a lot today is available water. And by available water, what I mean is simply the amount of water in each one of those assessment units that is available for either stream flow or groundwater recharge. This is the only formula that I'll show today, I promise, but just kind of the premise of available water. It's simply the amount of precipitation or the inputs into the system, the amount of potential evapotranspiration going out of the system, and then plus or minus the changes in snowpack. So as one of these assessment units accumulates snow in winter and melts going into spring and summer, that storage is going to change. So we ran these 5,600 assessment units with each one of these 6 different climate realizations. So this time series of maps for the state kind of shows you what's going on at a broad scale and kind of broad generalized scale. The climate projections, this is also only for one realization. So the climate projections are just for those I won't go too much into the details of the climate projection, but warmer temperatures throughout the year, increased precipitation in the winter, a decrease in precipitation in the summer. As a result, you see an increase in water available throughout from the onset of the rainy season in November moving into March. As the climate begins to dry up moving into the year, you see a loss of available water for groundwater recharge and for stream flow. This is in particular in the Cascades, where a lot of this precipitation accumulates as snowpack. So even though you have an increase in precipitation, the increase in temperature is going to make proportionally less of that snow, or less of that precipitation fall as snow and accumulate as snowpack. As compared to eastern Oregon, in the Wallowas, you have a more drier continental climate, where an increase that typically that suggests that an increase in temperature won't adversely affect snowpack. So you have an increase in precipitation. That precipitation is still going to fall and accumulate as snow, and you see an actual increase in water available moving into June and July. Again, this is a broad scale understanding of what's going on with the map, and let's look at what happens in a time series. So, and this is the mean of all 5,600 of those assessment units. On the vertical axis, you have the change in available water from the mean. So going from the 1971 through 2000 record with the climate change projected. And this has all 6 of the climate realizations applied. So again, we have an increase in wintertime precipitation. What this suggests is that you're going to have more water available in December, January, and February. Moving into the spring and summer, you have a decrease in water that's going to be available. Now, this decrease is partially because there's going to be less precipitation. But remember, groundwater storage, remember water available factors in the changes in snowpack. So you have an increase in wintertime precipitation as less precipitation falls or accumulates as snow, and that translates to less water available in the summer, which is what we saw on the maps as well. Well, this is just for the whole state, but we have this discretized into over 5,600 watershed assessment units. So let's look and see what that looks like. So this looks at the Nehalem River. The Nehalem River is in northwestern Oregon, is in the Coast Range. So it is a rain-dominated system, has a very minimal input of snow. So rain-dominated. On the vertical axis, you have the amount of water, and you have the runoff based upon that 30-year average. The orange line represents the available water. So when you have more water available, the difference between the runoff and the available water is simply the amount of water that's moving into the ground or being stored as in the soil and groundwater. If you were to subtract the difference between the runoff curve and the available water, that's water that's being gained in groundwater recharge, recharging aquifers. What does this system look like when you apply these climate realizations? Again, on the vertical axis, we have the change in available water from the previous normal. An increase in precipitation in winter. You're going to see an increase of water that's available in the winter months, so an increased likelihood. It suggests an increased likelihood for flooding. And moving into a spring, you see an actual deficit of water. Now, this can be explained by changes in temperature. The changes in temperature are going to increase potential evapotranspiration. As a result, you're going to see less water available within the spring months. This begins to flatline or come back to normal in the summer months. Remember, this is a rain-driven system, so this is a departure from normal. So normal in the summer is almost bare bones flow. So the system is still going to drain out of water and reach kind of that normal pattern within the summer months. Now let's contrast Nehalem with the Sandy River. The Sandy River lies on the western slope of Mount Hood. So here's Mount Hood. So it's just behind all of us. The upper portions, represented by the purple, are going to be more snow-dominated and receive quite a bit of precipitation and snowpack. The lower grayer portions are going to be somewhat of a rain and snow mix, but for the most part are going to have a much more stronger rain signal. Again, someone stole my millimeter sign, but this is this is good water of a depth of water. The runoff curve, you see as the wet season begins, you see an increase in runoff. It kind of somewhat declines, but it holds steady even though precipitation tapers off, and this is the result of snow moving through snow melt and sustaining flows. Consequently, you have available water increasing with the onset of the rainy season, but then it decreases. Remember, this incorporates snowpack storage. Right? So as you get to see water stored in snowpack, it's not available. And it becomes available again coming in April and May. And you see that increase. If you integrated the two lines and subtracted the difference, or found the difference, that would be water that's going into groundwater recharge. So what do these 6 climate realizations mean to a stream with a strong snow signal? Not surprisingly, you see a pretty big input, a pretty big pulse in the wintertime with available precipitation. This is a result of two things. First off, you have an increase in precipitation. Secondly, proportionally less of that precipitation is falling as snow and accumulating in the snowpack. As a result, you see almost a 200 millimeter deficit from the normal in the summer. This, again, increased temperatures, but primarily is because there's less snow stored within the system across all 6 of the climate realizations. So why do we care? This hydrologic classification system. Remember, one of the goals is to do, I showed 2 kind of context-based watersheds, but what does it really mean for a state? How do we use a hydrologic classification system? Again, it's going to give you the hydrologic characteristics, the climatic hydrologic characteristics of watersheds across the state, and really highlight areas that are going to be more sensitive to projected climate change, maybe in terms of flooding, increased likelihood of flooding, and also increased likelihood for drought. Also begins to tell you a lot about ecosystems and potential areas where ecosystems can be impacted or changed, altered. So this tags along a companion study of a fish biologist I work with, Joe Ebersol, and he went through eastern Oregon, so a very dry place, and found, mapped out where cold water refuge, so in a dry stream bed where there were cold spots within that stream. And basically where he found the presence of cold water refuge was directly related to that May surplus. That May surplus has a really strong impact on stream temperatures in eastern Oregon. This slide washed out, but within the circled area, there are hundreds of juvenile salmonids, and coming in this way is one of those cold water refuges. So what happens as you apply this change in climate? So that here the S prime is the available water. So you have a decrease in water over a lot of the state with regards to available water. But in other portions of the state, you actually have an increase in available water. So the changes of climate are not going to be, are not uniform across the state and across time. This also has a big influence on the human component and human consumptive needs for water. Eastern Oregon is a very agriculturally intensive, has a lot of intensive agriculture across the region. And if there's not water available, does that alter crop production? Does it alter your long-term planning for farming? Some regions actually have more water. Other regions lose quite a bit. So this is kind of a broad-scale approach at understanding how different watersheds are going to respond to the climatic stressors. So we did this initially for Oregon, and we're in the process of doing this for Idaho and Washington as well. This hydrologic landscapes approach, it really provides a classification system that allows you to understand how different hydrologic units function from a hydroclimatic input or perspective. And then also, how is projected climate change going to alter how a watershed behaves? It steps away from a deterministic model that's very computationally intensive. It simply uses monthly inputs, so it's pretty quick once you get it set up. The results, looking across Oregon, it varies. Some regions are going to have less water available, some are going to have more. And that really provides some insight into future management strategies in the region.